The last example to conclude this subsection is the conjugate or the adjoint operator of the convolution operation. Okay, suppose we have a function which is in L1, and we have a p that is greater than or equal to 1. Then we define the convolution as we did before. The convolution called CK, but CK is actually just a convolution using the K as a kernel. So CK is from LP to LP. Okay, so what it does is you take any LP function, which is just the convolution of K and F, and then we evaluate it at, so you evaluate it at point X. It's just the integral of Kx minus y f of y dy. Okay, and it is pretty easy to show that this is a linear operation, right? The CK is a linear operation applied to this. And we also want to show that the CK is bounded, but that is clear from the Yang inequality. We know that this, the one norm of this, sorry, I should say just since it's a mapping in our P space, so it is in our P, and we know that this is just the KF P norm, and it's less than or equal to the one norm of K and the P norm of F. So this implies that the CK as an operator, its operator norm is bounded by the one norm of K. So it's linear and it's bounded, so it's continuous. That's why the CK is in, we call this thing as X, CLX. Okay, so that's that. And now let's just consider what is the adjoint operator of CK. I'm going to claim that the adjoint operator of CK is nothing but just the convolution using K tilde, where let me write it down. So I'm going to claim that the adjoint operator of CK, as we just defined above, it is the convolution of using the K tilde as a kernel, where the K tilde is nothing but just K negative X. Okay, and to show this, we just need to check, let's say the G CKF. This is by definition. So G and F are in L2, LPR. Yeah, LPR. Okay. The G, I should say this. G is not. G is in LQ. So this is in LQ. R. This is in LP. R. Okay. So after the mapping by CK, it is still in LP. Okay, then we have the CK. We know that CK is just a convolution of F with K. And by definition, this is just the integral of G, say Gx, integral K x minus y, Fy, the dy dx. Okay. And then we can exchange the order of integration, again by Fubini theorem. We have f of y integral kx minus y gx dx, and then outside I have the dy, and then the integral, the inside is by definition, inside I can change the k to k tilde, and then I need to change, I put a negative sign of the argument, I have the gx dx, and then dy. Okay, and this is nothing but just the inside, just the convolution of k tilde and g applied to y, and then dy. And this is just this right now is in RQ, this is in RP, so this is the f of RQ is in the front, so this is the k tilde star g and f. Okay, and then we're done. So because this is just say k tilde g, or applied to g, and then f. Okay, and we didn't specify what the f and g are, so it works for any f in RP and any g in RQ. And because this is true, that means the ck tilde is just the conjugate of ck. Okay, that completes the proof. So this is the adjoint operator of convolution operation. Okay, so that's all for this subsection. So next we're going to talk about the convergence for functionals. So we talk about, so let's say the weak and weak star convergence. So let's first talk about the weak star convergence. So this is the pretty important concept for linear operations, or linear operators. Let's say we have, this is for weak convergence. So let's say we have a sequence. So let's say first we have a B star space, and then we have a sequence xk, which is in X. We also have x naught, which is in X. Okay, then we say xk is said to be weakly convergent to x naught. We denote this by xk to x naught. So the notation here is slightly different from the arrow. The arrow is like this, but this is just that. Okay, it's like a harpoon. And this notation denotes means that the xk convert to x naught weakly, or weakly convergent to x naught. If the condition is if for any f in x star, so any bounded linear operator, bounded linear functional, there is for any bounded linear operator, linear functional f, there is f of xk as a number. So this is the in R, okay? It converges to f of x naught. So that means xk may, the xk as a sequence will converge to x naught in the sense that if you evaluate that xk using any bounded linear functional as a number, as a sequence of numbers, f of xk converges to f of x naught. Okay? In this case, we call it the weakly convergent. Okay, so in contrast, what we had before is we say that xk is said to be strongly convergent or just convergent. Strongly convergent to x naught. In those cases, we denote this by that, right? And this means Well, the easiest way is to show that is to mean that this goes to 0. Okay, so in this case, it doesn't need any help of bounded linear functional. Just look at the sequence xk, x0, and the space x itself, and then you just check if the norm of the difference goes to 0. So this is the norm in the x space. It doesn't need help from x star. And the weakly convergent means that if you use any f there, then you get you can evaluate that, and you evaluate the f on this. And for any f, this converges, and that's the weakly convergent. Okay, so that's the difference of the two. Okay, we're going to take a closer look about the weakly convergent sequences and see what's the connection with strong convergence and what is the property of that. But at this point, you can imagine that the weakly convergence is weaker than the strong convergence. And how weak it is, we need to consider several cases. So first thing you need to we should be noted is that these two convergences are actually the same if we're working on finite dimensional spaces. Okay? So if the dimension of x is finite, then the two are the same. The weak convergence is just the strong convergence. Weak convergence implies strong convergence. Okay, this is not, in general, not true, as we'll show as examples later. The strong convergence implies a weak convergence, but the weak convergence does not imply strong convergence in general. But if the space is finite dimensional, then we can show these two are the same, meaning that a weak convergence also implies strong convergence. And the reason is, say if x is a finite dimensional, that means I can find a basis, complete basis for x. Say x is n-dimensional, then we can let this be a basis of the x. So that means any element in x can be written as a linear combination of this basis, okay, in the complete orthonormal set. Okay, so in this case, for each xk in the sequence xk, I can denote it by a linear combination of the bases. So let's say the coefficients are the a1k e1 plus a2k e2 all the way to the ank en. Okay, this is assuming the dimension of x is equal to n. Okay, and this k is the index for the iterate in terms of the sequence. So that's for that, and then the limit, we can also write it as a linear combination, which we write it similarly in this way. Okay, so now let's see what is the meaning of xk converging to x not weakly. In this case, let's see. Let's say that I'm going to define fi such that the fi ej is delta ij, meaning that if I is equal to j, then we get a 1. If I is different from j, we get 0. Okay, we can always do this. The easiest way is to see this, well, there are different ways to see this. The easiest way to see this is perhaps, say for E1, you can define, if we consider x1 to be a times E1, where a is the number, and then you can define the f1 to be defined on this linear subspace x1, and takes any element in here to just a. Okay, And in this case, you can extend this to the whole space. And because this is E1, because E1 is perpendicular to the space spanned by the other bases, it will be easy to show that the F1 will be 0, will take 0 value at all the other bases. That means the F1, in this case, it would imply that F1 at E1 will be 1, and F1 with EJ will be 0 for any J not equal to 1. Okay, so you can do that for the first basis, then you can do this for the second basis, E2, so on and so forth. Then you get for each basis you have this Fi, okay, and this it satisfies that. But in this case, what you can say is because this Fi is in X star, so because of the weak convergence, we know that Fi of xk, this is equal to, say you're applying Fi to that, and that's Fi to whole thing of this, because it's linear, so Fi is applied to each one of them, but it only, everything cancels except the Ei. And the Ei, if I apply this to the Ei, then you only have the Aik left, right? So this will be Aik left. So if you apply Fi to xk, you get that. And you have Fi to x naught. So I should say case subscript. And you have Ai 0. And you know that because of the weak convergence, this should converge to that. As a sequence of numbers converge to that, and that means this converge to that. Okay, so that means the coordinate coefficients converge. Okay, the corresponding coefficient converge. So that means this converge to that, second one converge to this, so on and so forth. So they are as numbers, real numbers to converge. Okay, so this is we obtain this because that xk converge to x weakly. And from there, we know that we look at the xk and x naught, just directly look at their difference. This, according to our definition for xk and x naught, is just the sum of sum of ai k minus ai 0, ei, I is from 1 to n. Apparently, this is by triangle inequality. This is less than or equal to the sum I from 1 to n, and then ai k minus ai naught times the norm of ei. But this is just a 1. So essentially just that. But we know that as a sequence for each index I from 1 to n, this thing goes to 0 as k goes to infinity. Okay, for each I, you have this, and so the sum of them still goes to 0 as k goes to infinity. And this just means that this is strong convergence indeed. So xk just converge to x naught in the classical sense, or a strong sense. Okay, so this convinces that the weak convergence is just a strong convergence if the space is finite dimensional. Okay, but in general, I should remark that it's not necessarily true. Okay, in general, the weak convergence is weaker. Okay. So we're going to show this soon later, but first, since we have the weak convergence, one question is if this limit is unique, because it's weaker. So is it possible that the xk converge to weakly converges to x, and also it weakly converges to something like y? And the answer is no. The weak limit is still unique. If the weak limit exists, then it is also unique. If it exists. Okay, the proof is pretty simple. You just think that if that's not the case, then since xk converge to x, and weakly converge to x, and xk weakly converge to y, and this means that for any f in x star, the f of xk as a sequence of numbers convert to f of x. At the same time, f of k convert to f of y because of the weak convergence above. Right? But as a sequence of numbers, they converge. That means they must convert to the same thing. That means f of x must be equal to f of y. Or in other words, f of x minus y should be equal to 0. And this is true for any f in x star. But we proved before that there must be enough bounded linear functionals that can distinguish the elements. So an element is 0 if and only if an element z is 0, if and only if f of z is equal to 0 for any f. And this is the case, right? Because this is equal to 0 for any x, that just means that x is equal to y, or x minus y equals to 0. Okay, so that's why the limit must be unique. Okay, the next is what we mentioned earlier. The weak convergence implies strong convergence. Oh, sorry, the strong convergence implies the weak convergence. So if we have this, then the xk convert to x weakly. Okay, use this. Well, the proof is also pretty easy. Suppose we just look at f of x k minus f of x naught. We want to show that this goes to 0 as k goes to infinity for any f. Okay, so these are just a sequence of numbers, but because f is linear, so we know this is just bounded by the norm of f times the xk minus x naught. But for any f in x star, we know that this is something finite, and that this thing goes to 0 since the sequence converges strongly. So that's why the whole thing goes to 0. And this means that f of xk goes to f of x naught, and by definition, we know that xk goes to x naught weakly. Okay? So xk convert to x naught weakly. A strong convergence implies weak convergence. Okay. So now let's think about an example, in which case we can indeed find an example that are, or find a sequence that is weakly convergent but not strongly convergent. Okay, let's look at this example. Say we have L2 space. So it's L2 over the interval 0, 1. And then let's say we define xk to be sine of k pi t. Okay, and t is between 0 and 1. And apparently the xk is square integrable. Okay. Now actually, by Riemann-Lebesgue theorem before, so what this one is, this is actually one of the homework examples we had in a real analysis class. It says that if you have any L2 function, f, and then you take the inner product with this xk, which is essentially just the integral of the product, which is sine of k pi t dt. We know that when k goes to infinity, this always goes to 0. Okay, so because this is 0, 1, so this is the first x1, and then x2 is this. Right? And then when k goes to infinity, this oscillation is higher, and then when you take an integral, we'll multiply this to f and take an integral. Then kind of things cancel out, and then you can just get 0. So this goes to 0. This is what we proved before, as k goes to infinity. So for any f in L2, this goes to 0. Remember, this is nothing, just L2 star, because the dual space is the same as the self. For p goes to 2, right? So this means that, by definition, this means that sk goes to 0 weakly. Okay, xk goes to 0 weakly. However, when you look at xk minus 0, okay, if this goes to 0, xk goes to 0 strongly, or converge to 0 strongly if and only if this goes to 0, right? But we'll look at this. It's xk, but that's just the sign of k pi t. We know that this norm is just taking the maximum, taking the square root value, just integral of sine k pi t square 0, 1 dt, and this 1/2. And we can show that this is actually equal to 1 over root of 2 for any k, no matter how large the k is. For any k, we have that. And that is not going to 0. So that means xk is not converging to 0 strongly. Okay, and this actually this xk doesn't converge. If it converges to something, if xk converges to some x naught, then we know that xk will converge to x naught weakly. And because the weak limit is unique, that means the x naught is equal to 0. But we already showed that that is not the case. It cannot converge to 0 strongly. Okay, so in this case, it doesn't converge strongly at all. Okay, so that's what happens in general. So weak convergence does not imply strong convergence in general. But there's a theorem or lemma. I write it as a theorem here, due to Mazo. He said that if we have let me show you what the result he can get. Suppose we have a B star space, and we have xk converge to x naught weakly. Well, in general, we cannot guarantee that xk converge to x naught strongly, but there is a way to make a convex combination of this sequence such that these convex combinations converge to 0 strongly. Okay, so that means, or in other words, say we have x1, x2 all the way to xk, and they're only converging to x naught weakly. But for each k, you can make a convex combination of the previous of the elements, so that the you can make a convex combination of this. Means that you can have lambda 1 times x1, lambda 2 times x2, all the way to lambda k times xk, where the lambda i's are non-negative and they sum to 1. So make a convex combination, lambda I xi, I is from 1 to n. Then this thing will converge to the x naught. So you can define this to be yk, so it's yk, which is defined in this way, and that depends on what the lambda is. I have to emphasize, lambda I may change, but this will converge to x naught strongly. Okay, so that's the claim by Mazu. Then for any epsilon greater than 0, there exists lambda I greater than or equal to 0, sum of lambda I from 1 to, I should also say that there exists n. Such that this is equal to 1, and the sum of lambda I xi, I is 1 to n, its distance to x naught is less than epsilon. Okay, the proof. So this just we just need to show that we just need to show that this M as the closure of the convex hull. Let's say convex hull of xk. This is all the possible convex combinations of xk, and we can take a closure. You can take a closure here or above. It's the same. We showed before that they're the same. Let's say the M is this. Okay, and then we know that this is a closed and convex set. The M is a closed convex subset of x. Okay, and what I want to claim is that this m is just x. Okay, maybe I should say, yeah. Let me change this to. I think it only works for Banach space. Okay, so m. I want to claim that m is just x. If not, if x, say x naught is not in m, and what happens is you call the theorem due to Ascoli. It says that m, say m is this is the I think it's one of the corollaries of the Hahn-Banach theorem. So you have m which is closed convex, you have some x naught which is not in m, then there exists a separating plane. Okay, there is a separating plane, and that strictly separates the two. So that means there exists some f in x star such that, and also some a, such a is a real number, such that the f of x naught is greater than a and is greater than f of x for any x in M. Okay, and apparently all those sequence xk, they're in M because M is just a convex closure of the convex hall. So every xk is in there. So this is also true for any k. And that is a contradiction because we know that xk converted to x naught weakly. So that's not possible. They cannot be separated by some number, right? So this is the f of x naught. This is the a, and you cannot say that the f of xk lives in here because the f of xk is supposed to converge to f of x naught. So this is a contradiction to that xk convert to x naught weakly. Okay, so that means that this M is actually the whole space X. Okay. So now we know that we know what's the properties of weak convergence. It's the several simple properties we have seen before, but it can be useful. It can be very useful if we cannot easily show that sequence converges strongly, but we can use the help of the X star, the dual space, and that is we can check if it's weakly convergent. Okay. So from there we can extend, just as we did for the bidual, we can extend a little bit. Say we have the X, which is a B star space, and then when we have the X star, which is a Banach space, right? And we can consider the weak convergence in X star now. So we can see that Fk convert to F weakly if, so we say Fk convert to F. So they are all in X star. We say this convert weakly if the, in this case, we need to show that the X double star, this X double star has nothing to do with X itself. It's just something in the bidual. Okay, if for any X double star, there is X double star of Fk convert to X double star of F. Right? If we use the same definition before, but just treat this as our X and this as a sequence in X, then the weak convergence just means this, right? Okay, but the question is, sometimes we don't want to deal with things in bidual because it's even more. We need to do it in an even larger space. It's the X. it's okay, X star, that's all clear. But working on this is more troublesome. And we know that X is just simply a subset of that. Okay, so we actually expanded X to a larger space, and that is not always possible or easy to handle. So how about we just restrict ourselves to X only, not to X star? So that means here, if we change this to a new type of convergence, so this is what we have here is the weak convergence as we defined before. But now let's say we have this. If we know that the any X in the space here can be mapped to an evaluation map, or anything here can be mapped to evaluation in the BIDU, which means that X is isometrically embedded into the BIDU. So this is a subset of that. Let's say that if for any X in the space X, there is fk of X converge to f of X. Notice that right now the changing sequence is f, not on X. If this is true for any X, then we say the fk converge to f, or is a weak star convergent to f. So in this case, it's not just a weak, but a weak star. Okay. So usually we write it either in the weak star convergence, or we sometimes write the weak star limit k goes to infinity of fk is equal to f. Okay. Sometimes you can write it in this way. It means that it's a weak convergence and a weak star convergence. And the weak star convergence is even weaker than weak convergence, because as you can see here, you actually require anything in the X double star to have this to work. Okay, but here you just need the X which is in this case, that you can think of this as the Jx of fk convert to the Jx of f. Right? That's what this one is. And this is the even weaker than above, because right now you only ask for the X in the X space. And here you want this X double star to be in this even larger space. Okay? So the weak star convergence is even weaker than the weak convergence. Okay, so that's the weak star convergence. But even though we can still show that the weak star limit is unique, if the weak star limit exists, it must be unique. And the weak convergence implies weak star convergence, as you can see obviously. And moreover, let's see, let's try to use apply the Banach-Steenhuis theorem we had before to show that, say, remember there we have a tk of X converge to, say, tk is a sequence tkt, they are all in L, xy. Xy are Banach spaces. If this is a convergent, if and only if the tk is bounded, right? It's bounded by some m for all the k, and also the tk, this is true for any x, if and only if the tk itself is uniformly bounded, and the tkx converge to tx for any x in M, and the M is a subset of X which is dense. So it has to be a dense subset of X. That's the Banach-Steenhuis theorem. So we can use that to get the following results. The first result is, say we have a B star space X, and xk, X they are in X. Then we can claim that the xk converge to X weakly if and only if the xk is bounded by some, I should say this is a different number, it's finite. I should say maybe should say this should be bounded by some constant C. Okay, and also in a dense subset of X, that TKX converts to TX. Okay, so that's this. And then going back to our theorem, xk converges to x weakly if and only if xk itself is bounded by some constant, C. And secondly, the fk, so f of xk converges to f of x for all the f, I should say for all the f in M, the M star. So M star is not dual space, M star is just some set, which is a dense subset of X star. So the theorem says this: we have a B star space, and then we have a sequence xk and the limit x. So the xk converges to x weakly if and only if the sequence xk itself is bounded. Okay, and also for a dense subset of X star, which this dense subset is denoted by M star, or you can call it N or something else. Just some, it's a notation together. It's in the X star, so that for any point in the dense subset, we have f of xk converted to f of x. Okay, so this is direct application of the Banach-Stevenhaus theorem, because in this case, we can just identify the xk with its evaluation map. Okay, this is because the right-hand side, the 1 plus 2, so in this case, we just think that this xk right here is the j of xk. Okay, and that is, we know that it's in x double star. Okay, and here, this is just the j xk at f. We convert to j of x at f. Okay, and this, we said this f is a dense subset. It's in a dense subset, just like here, the x is in a dense subset. And the tk is a sequence, which is j of xk and j of x. And we know that they converge. And also j of xk is self-bounded by that. So that means the j of xk, according to the Banach theorem, the Banach-Stevenhaus theorem, this just means the jk of f converge to jxkf converge to jx of f for any f in x star. But this this item or this statement just means that f of xk converge to f of x for any f in x star. And this just means that xk converge to x weakly. Okay. And furthermore, we can consider this. Let's say we have a Banach space. Okay. And then the fk weak star convergent to f if and only if, first, the fk is bounded by c for the k for some constant c. Secondly, the fk of x convert to f of x for all the x in the M in X, and this again is in dense subset of X. Okay, and actually you can show the same thing. The 1 plus 2 just means that J of X, so the proof is that 1 plus 2 just means that the J of X of F convert to JX JFK, JX of FK and JX of F covers that for any X in X, right? And this means that the Fk of X convert to F of X for any X in X, and this just by definition is just Fk converge weak star converge to F. Okay, so the proof is just based on, it's just a simple application of the Banach-Steenhuis theorem. Okay. Okay, we can also consider the weak convergence for operators, not just the linear operators, not just the linear functionals. Let me give you the definition. So let's say X and Y are B star spaces. Okay, and then we have the TK, T, that are in L, X, Y. Okay, it's for any K here. Then we have several types of convergence. The first is called uniform convergence. Or you can interpret it as the strong convergence in the LXY space. If you treat LXY this as a Banach space, then what I'm writing below is just the strong convergence in this space. But we're given we call it uniform convergence. It's uniformly convergent to T if Tk minus T as the norm in the LXY space is going to 0. Okay, as k goes to infinity. So that's why it's a uniform convergence. Okay, Tk is said to be strongly convergent to T if the Tx, if Tkx minus Tx as they're all as elements in the Y space, in space Y. If this goes to 0, as k goes to infinity, for any x in here, we call it a strong convergence. Okay, so this is like the one in the Banach-Steenhuis theorem, right? The Tk evaluated at any x, the Tkx, it converges to Tx. Third, the last one is the Tk is called weakly convergent. Weakly convergent to T if f of Tkx converge to f of Tx as k goes to infinity for any x in the space X and any f in, remember that Tx, Tkx, they are in the space Y. So this f is in the Y star space. Okay, so it's a weakly convergent in that sense. So this is not, you should distinguish this from the one in for linear functionals. Okay, because here we evaluate that the Tx, Tk of x are still in Y. they're not real numbers. So if you want to say they are weakly convergent, we will still need the help of elements in Y star, or need the help of Y star. That's why we had a weak convergence here. Okay, strongly convergent is not as you expected. So this is not as a sequence of linear operators. We're not really we're not discussing this convergence as the strong convergence. Instead, we call this uniformly convergent. And the strong convergence means this. Okay, this converges to 0 for any x. Okay, and what we can show is that the uniform convergence is the strongest. Uniform convergence implies strong convergence. It's pretty easy to show, right? You can see about if the norm, even the operator norm, converges to 0, then it should converge to 0 for any x. So this implies that it's pretty clear. And also, if this goes to that, this is just a sequence in Y space. So this is like a strong convergence. The TKX convert to TX strongly, space Y. So that's why we apply this definitely work. So this also implies that. So strong convergence will imply weak convergence. Right? Pretty easy to show. And also, if the limit exists for each of these three cases, if the limit exists, it must be unique. Okay? It will be very easy to show. At least for the first two, it's really easy to show. And the last one is also easy to show, because if you have, say for the last one, I want to show that a weak convergent or weak limit is unique. Say if it's not unique, say if a TK converge to T weakly and the TK also weakly converge to S, then what happens is f of TKX converge to f of TX for any x and f, right? And also f TKX converge to f of Sx. They're all numbers. These are all numbers. So the convergence makes sense. And so that's why these two must be equal for any f and x. And this means the f of Tx minus Sx must be equal to 0 for any f in Y star and in any x. But if it's true, if this is equal to, for any fixed x, if this is true for any f, this just means that Tx minus Sx should be equal to 0. Okay, and if this T minus, this is just equal to T minus S applied to x. And if this is true for any x, that just means T minus S is equal to 0. So that's why T is equal to S. Okay, so the limit, weak limit is also finite, is also unique here. Okay, now finally we just give a few examples to say that the strict inclusion of this, that means in general we don't have that, in general we don't have this. Okay, so let's first show the strong convergence does not imply uniform convergence in general. Strong convergence does not imply uniform convergence in general. So we need to find an example where the sequence is strongly convergent but not uniformly convergent. Okay, so example is this. So we have L2 space. So L2 is just a sequence x1, x2, where the sum of xi square is finite. Okay, that's the L2 space. I'm going to define this mapping here such that for any x, which is equal to x1, x2, or which would be mapped to Tx, which is x2, x3. So just move everything to the left and then remove the x1. Okay, so that's the T. And now I define the Tk. This Tk just apply T for k times. I'm going to define my Tk operator in this way. It's defined as applying T for k times. So imagine that if you apply xk, you apply the tk to x, then what do you get? It's a sequence xk plus 1. You remove the first element for k times, then you will start from xk plus 1 now, plus 2, so on and so forth. Okay, that's the tk. Okay, and then we can show that the tk goes to 0 strongly. So that means, let's look at the tkx. I want to show that this goes to 0. That means this goes to 0 as k goes to infinity for any x. Okay, for any x in L2, the tkx score, say, is equal to, we know that it's just k plus 1 and so forth score. And this, by definition, is just xk or xj score, where j is from k plus 1 to infinity. But remember that the x is from L2. So that means this sum, the sum of the tail, will go to 0 as k goes to infinity. Right? So this means that tk converge to 0 strongly. Okay, so we know that is strongly, but let's see if it's uniform. To show it's uniform, we need to show that tk goes to 0 as k goes to infinity, or uniform convergence means that this should go to 0. But let's look at this. This is the tk norm. Okay, remember that if I apply the tk to, see, I denote ek to be 0, 0, 1, 0. This is the case 1. Only the case 1 has the value 1. All the others have 0. So if I apply the tk to ek plus 1, then I'll get e1, right? So this means that tk ek plus 1, on the one hand, it is equal to the e1, which is equal to 1. But on the other hand, it should be less than or equal to the tk norm times the ek plus 1 norm. Okay. Oh, by the way, this definitely is a linear, continuous linear operator, right? So you can see that, but this one is also equal to 1. So it just means that tk is always greater than or equal to 1. Okay, this is greater than or equal to 1 for any k. So that means this is not going to 0. That means the tk is not uniformly converging to 0. Okay, and actually it's not converging to anything because if tk converges some t uniformly, then it implies that tk converges to t strongly. The limit is unique, so the t must be equal to 0, but we already showed that tk is not converging to 0. Okay, that's the similar as before. So that's the example that weak convergence, strong convergence does not imply uniform convergence in general. And then we can also show that weak convergence does not imply strong convergence in general. Okay, we're going to work on with the same space, but with the redshift. So just fill in 0. Okay. So in this case, again, sk of x. So sk is defined as applying as k times. Okay, so first we want to claim that I'm going to claim that Sk converge to 0 weakly. And in this case, we just need to show that f of skx converge to 0 for any f in L2 star, which is the same as L2, right? And also for any x in L2. Okay, so the f is in L2, and because of the Riesz representation theorem, the f can be identified with some element of yf, which is in L2. So this is, let's say, it's just a y1, y2. Okay. And now, let's see what this is. So the f of skx is just the inner product of yf skx. So this, remember that is y1, y2. This is 0, 0, 0, sk, this is k of them, s1, x2. So taking the inner product of the two in the L2 space gives us the sum of yk plus I, xi. I is from 1 to infinity. Okay, and this is bounded by Cauchy-Schwarz inequality. This is bounded by 1 to infinity yk plus I squared 1/2 times this. And this is just the norm of x. And we know that this goes to 0 as k goes to infinity, because this is the fixed vector yf here, and that's in L2. So the tail, the sum of the tails goes to 0 as k goes to infinity. So this indeed goes to 0. That means as k goes to 0 weakly. Okay, and next we show that xk not converging to 0 strongly. And why is that? Because, let's see, if we convert to x0 strongly, then for any x, I should have this goes to 0. But this is just the skx itself, and that is just the norm of x. Okay, it doesn't change the norm since it's just right shifting, but take the L2 norm, it's still the same thing. Okay, so this means that it's not converged to 0 strongly. Okay, so in general, weak convergence is indeed weaker than strong convergence.